And one of the things you guys hate, there will be a bunch of plug and chug problems, right? Take derivatives, do stuff like that. We'll go through some of those. But you can also come back to problems on chapter 2 or chapter 1. Stuff like this, you know, find the limit as x approaches 3 of f of x equals 2, where f of 3 does not exist. All right? And we can do this. All right, and start creating a function. I'm going to do it in a different color. You know, and start making a function. So like up here, I just did this, right? I created a function that has a limit but doesn't have a value. All right? And then I'm going to jump down and do this next, okay? And I can define left-hand and right-hand limits, right? I could say, as you approach it from the right-hand side, it equals -1. So at 4, from the right hand, it's -1. From the left-hand side, it equals 0. Maybe I'd connect them like this. Get rid of this. All right? And I said f of 4 equals 2. Boom. Right? And that's still a function. So now I've graphed this portion and this portion. I think the thing you guys probably don't know as well would be a question like this. At x equals -2, let the limit equal 4. So -2, 4. There's the limit. And it says that the derivative doesn't exist. You guys remember we talked about this a little bit. We can have a derivative or a continuous function, okay, and have it not have a derivative if it looks like this. You guys remember this? So if I do this, I just created the conditions up there, all right? I created a limit, and actually what I did is I actually graphed that f of 4, or f of -2 was 4. That's what I meant to write there. That there's a value at that point, so it's continuous. But at the same time, it doesn't have a derivative, okay? Oh, up here, all right? To tie these two together, I'm sorry. We can have functions that don't have a derivative when they come here, because derivatives are simply limits, right? And we don't know if it's that one or that one. And when you have a curve where you can't write the single tangent line at a point, the derivative doesn't exist. All right, now the derivative would exist here, obviously, right? And it would exist everywhere else. It is not this. Okay, because that curve, this curve is not like this. I agree the derivative here would be 0. Okay? So again, we can do a limit, curve, stuff like that, okay, as we go. There is a lot of problems like this on the test. All right, and I'm sorry about the quality of picture, guys. It's orange. Where we're going to ask you, you should be able to estimate slopes of derivatives from curves. Okay, we haven't practiced this for a long time. But like here it says f prime of -3. So let's make my graph a little better. -1, -2, -3. You know, I would graph it here, and I know that that this line is 45 degrees is 1. So I think it's a little steeper than 1. Maybe it's like 1.25. Maybe it's 1.5. I don't want to really take the time to figure it out right now.
Wait, wouldn't it be, why isn't it 1? Isn't it 3 over?
Well, I see it here.
2 over 2.
I see it here. Yes, it's a little steeper than 1. All right, Sam, because I get what you're saying, Sam. Do you see that? You see this line right here in the corner I just boxed?
Yeah.
That's 1. So if I bring that up, I think the line's a little steeper than 1. See what I mean?
Yeah.
All right, so again, I just threw my reference line here in the corner. It's a little steeper. I'm not going to hold your feet to the fire. If you said it was negative, or if you said it was like half, or if you said it was like 7, those are arguments I'd have to have with you, right? There's a range of answers in this case. At -2, the next value, I would look to say that you at least thought it was a little less than it was. And I'd say that's about 1 when I draw it. That looks like the line in the corner I have as a reference. All right? F of -1, I only take one answer here, guys. I would actually write equals 0. That is a max, right? That crowns. It has a derivative. It's not a bird. F prime of 0, ooh, it's steep negative. steep negative. Ugh, I don't know. It's very steep negative. How about negative 3.5? I don't know. Negative 2.5.
How do you like give these up to it?
All right.
Yes.
Yeah. Well, all right, Sam. I guess I have a lot more experience making triangles. 1, I guess it's about negative 3. See what I mean? I just extend it out. And I suppose I could, so again, I take a lot of values here, so maybe it's negative 3. But I'm drawing the line by hand, which really hurts. And it's practice, Sam. I'm really good at this. F of 1. Oh, again, only one answer I'd accept. 0. At the minimum, it bottoms out. It definitely has a derivative. F prime 2. Boy, exactly. Does everybody agree? That's really, I might go approximate, but it is super close to 1. Finally, F prime of 3. I am looking that you understand that that is steeper. Does everybody agree it's steeper than the last one we did? So I would look for some sort of increase between these two. Does that make sense to you guys? Otherwise, all right, if you answered them both 1, I'd have to mark it wrong. If you said that this one was 0.9 and this was 1, I'd probably mark them both right. Because then you get into that little argument about what it is, okay? All right. So again, derivatives are slopes of the tangent line. That's the understanding. We can do it from a graph. Or we have learned all the rules, right? The power function, the chain rule, the trig derivatives, all that. So I could actually take problems like these two, and I'm just going to do the derivatives, all right? And the big thing that I usually find students struggle with, I am recording, aren't I? Yeah. All right, the thing I usually find students struggling with at this point is they forget to put it in fractional exponents, all right? Everybody, it's got to be this. And and that is not a hard derivative to take, is it? Now you do the power rule. So this was question, so I'll do it over here. Y prime, bring the power down. Half comes down, reduce 1/2 by 1, which makes it negative half. Plus, bring the 4/3 down. Subtract 1 from 4/3, I think you get 1/3.
For the second one, shouldn't that be a negative 4/3 just below?
Ooh, thank you.
But really ask about it.
No, I'm in a hurry. You're right. So that makes negative 4/3, which makes it negative 7/3. My bad. Holy cow. Going too fast.
Really?
Nice catch, Lily. Bonus point tomorrow. All right?
I won't take it this time.
Does everybody agree with that one? That's a little better, right? I screwed up when I put it. You gotta make sure. But again, classic example of things you can screw up, I guess. All right. On the next one. Oops. And I can go entire page here. Sorry. Everybody, you have to see this as the product rule. And I am sure this is on the test tomorrow. I haven't written it yet. Doing it this afternoon. But I guarantee you I'm putting that on there somewhere, where I actually ask you for the definition. And we've used it enough, this should not seem like a challenge. All right? So if I want to find the derivative, and again, I don't believe, I'm just going to say the first one is f, the second one is g. So I do f prime of 2x, which is 2. All right? Whoops. That was weird.
What's that?
That was mental math. I do it the other classes.
Oh.
All right. I just hit the wrong tab. All right. Plus. Now, do we all agree this is x plus 1 to the half power? Right? That radical. And I got the sign right this time. Positive half. All right. So on the next one, it's 2x. Now I have to do the chain rule on this. Now I know the derivative inside is 1. But realize we're doing the chain rule. Times 1/2 x plus 1. Half minus 1 is negative half. Times the derivative of the inside. Derivative of the inside, do you all agree it's 1? And again, tomorrow I'll probably have different examples like this, all right? And if I say simplify it, you would at least have to get here tomorrow. I would write this as, that would be simplified enough, right? We take 2 times a half and the 1 and just write it that way, so the coefficient's there. All right? These problems get a little more complicated, guys, if I have some sort of non-integer derivative, you know what I mean? If I put x squared in here, it really only changes this last portion. Do we all agree? I mean, that fast. I can change this problem to that by putting the green x squared on there, and all of a sudden that's the only change. Did everybody follow that? Because the inside derivative changed. X squared plus 1 has a different rate of change than x plus 1. All right? So again, derivatives like this, quite a few. First derivative and second. I could ask you to take the second derivative of either of these, I would think. This one would be a little harder. Do you agree? Second derivative of this would be a little bit more difficult.
How'd you get to x plus 1 for the very first?
All right. On the original problem, it was 2x times x plus 1 square root, right?
Yep.
The derivative of 2x is
Oh, okay, yeah.
2. All right. And then this stayed the same because I made that the g. Does that make sense?
Okay, got it.
All right. Again, you can practice this. All right. Boom. Which takes us into problems like these. Now these you haven't been. I've seen some. I noticed some problems on the homework with this. All right. The first thing you got to catch here is this is a trig derivative. All right. The second thing you got to catch is it's going to be the chain rule, because all you know from your memorization or understanding is you guys know tan x is secant squared x, right? That's what you know. But there's a whole, the argument is not x. The derivative of the argument is not 1. So it has to be the chain rule. Okay? And the chain rule, again, if I put it on the board, if I have f g of x, and I say I want the derivative of that, it is f prime g of x times d prime of x. Okay? So these are the 2 rules in black for this red problem, okay, that I need. I'll shrink them down and give myself some space. So if I change colors to blue, I do not do the U substitution. I hope you've been practicing enough not to. I don't really want to write this as y equals tan u, where u equals 1 minus x to the half.
Wait, I can't see.
Really? Am I too high?
No, this is not. Oh, very on. Very on.
Wow, that was weird. Okay. I really don't want to do it this way. If you have to tomorrow, you can, but I'll level with you. It'll slow you down to a crawl. There's a lot of problems to get, a lot of derivatives to get through. So I'm going to do it the way I want tomorrow, okay? This would work, though. You can do dx. All right? So what I'm going to do on the simple ones, because I'm not going to have a chain rule of 3 tomorrow, okay? Those are coming. We got practice more before we start doing those. Y prime equals derivative of tangent is secant squared. The argument stays the same times. Now I have to take the derivative of the inside. I have to take the derivative, and again, I see that you guys agree it's 1 minus x to the half power. So I take the derivative of that. The half comes down. 1 minus x. Take away half. And now I have to take the derivative of the inside of that. This is a 2 chain. What's the derivative of 1 minus x?
1.
Negative 1 because it's negative x. X is 1, you're right, but the negative comes with it. And that's the derivative. And I would guarantee on this one tomorrow, I would say, please don't simplify. It would say, don't simplify. So I would stop right here tomorrow. If it asks you to simplify tomorrow, you'd have to do negative half. The truth is, it's not that much different. I suppose just combine the half and -1 this time. All right. I don't want you to get thrown by different variables. We used x and t a lot the last couple of weeks. I never thought about putting in theta. So I could write g of theta equals theta times sine theta. Okay? And I could ask you to evaluate g double prime at pi over 6, or the second derivative at pi over 6, right? And again, this one is a product rule. All right? I'm going to identify f and g. All right? And I'm going to say g prime of theta equals, derivative of theta is 1 sine theta. You don't have to write the 1, guys. But believe it or not, I do a lot of times because I like to prove in my head that I took care of it, that I have f prime g shown right now, f prime g. And now I'm going to do g prime f, g prime. Derivative of sine is positive cosine. Okay? And now I have to do the second derivative. And maybe it's something I should have said before I did the first derivative. I immediately knew, because it was a product rule here, that there would be 2 terms in my derivative, right? Separated by an addition sign. Likewise, right now, going to the next derivative, I know that there's going to be a 1 term for this derivative, and there's going to be 2 terms for that derivative. So I'm going to have 3 terms in my second derivative. Hopefully everybody sees that right now. Okay, because I got just a regular derivative here, and I have the product rule again here. All right. So here I go. Take the derivative of sine, which is positive cosine, right? All right, chain rule. And fortunately, it was addition here, okay? If it was a subtraction, you have to distribute to both terms, okay? But it's the chain rule of that. So again, 1 times cosine theta, fg, f prime g, plus g prime f, or f. And the derivative of cosine is negative sine. Oh, I got some like terms. And even though I'm evaluating, I think I would take the time to write this at least to make my life a little easier. All right. Now, this keeps us going. So now I have the second derivative. I want to evaluate it at the value. I'll go to red. It matches that. Oh, look, somebody's getting a note from the principal. Lily is misbehaving. All right. So here we go, guys. Plug it in. We'll keep trucking today.
Oh, sorry, that's not bad.
That's all right. I'll pick on Lily again tomorrow, okay? I promise. All right. Now listen. You can use your calculators tomorrow, but very shortly I'm going to have a no calculator test on stuff like this. So this is one. This is one we should know. Pi over 6 is 30 degrees. Do we all agree? Because 180 divided by 6, pi radians is 180 degrees. So this is this. So I can do this out exactly. 2 times cosine of pi over 6, which is square root of 3 over 2, minus pi over 6 times sine, which is 1/2. So my final answer.
Alex, go to the office, please.
Yeah, different Alex Gobley, Sam.
Oh, they could hear me. Oh, crap.
It's good you didn't say anything bad about me. Whoop-da! There we go. Tomorrow I would take the decimal. I would, because you got a calculator. You guys agree? But I am going to tell you, when you think about con and where you're practicing, you definitely want to be practicing exact numbers, all right? So, classic example, again, a lot of work, right? It has to be evaluated at a spot. Right. Next problem. Find the equation of the tangent to the curve at the given point. All right. Again, find the equation of the tangent. That means find the equation of the line, which means you need slope and a point. I gave you the point, or the problem gave the point on both of these problems. There's 2 of them here, 1 and 2. I'll box this up or move this one down. You already have the point. You need to find the slope. You need to find the derivative and evaluate at the value. I need to find y prime when x equals pi over 6. I need to fill in that blank so I can do an equation of a line. All right? And again, this here is a chain rule. All right? It's a chain rule. We don't know the derivative of sine squared. All right? We know the derivative is this. Remember, I know this is just this, right? All right. I'm not going to write that, so we have to do the derivative first of the square. So y prime is 4 times 2. 2 minus 1 is 1. So just sine x times derivative of sine is cosine x. Now I'm going to go times. And again, you got to remember, the argument here is times 1, because the derivative of x inside would be 1. If you have a derivative later, if you have a trig function like this later on, where this isn't x, you'd actually have to do one more derivative, right? All right, so this is our value. 8 sine pi over 6. We just put this circle up on the board, or circle, the triangle, I'm sorry, from the unit circle. We know sine of pi over 6 is 1/2. We know cosine of pi over 6 is square root of 3 over 2. So I think when I get this, I get that this is equal to 2 square roots of 3. And again, tomorrow you'll be able to use a decimal, okay? So if you want to plug that in and make sure your calculator's in radians, right? But I'm also going to be coming to exact values. And I said find the equation of the line. I'm going to use point slope form. Y minus 1 equals 2 square roots of 3 times x minus pi over 6. Again, point and slope. Point and slope. All right. All right. 47. So again, I want to do another one of these because it's just good practice for you to see. Find the equation of the tangent line to this function at this point. All right. Now, everybody, I could have said find the equation of this line at x equals 0, and you'd have had to plug it in and calculate that y was 1 to get the point. Right? And we did some of that a couple days ago, right? Where I just gave you an added value and you had to find the point too. But this time we just have to find the slope of the tangent, which means take the derivative and evaluate at 0 this time. So we're going to do y prime evaluated at x equals 0. I need that slope. Okay, what time is it there?
45.
Okay. I'll get through a few more. Does everybody agree? And again, I skipped a step here. I skipped a step. If I start the derivative, it's not done. The derivative's not done. But does everybody see that I changed the radical to a half power? And I did the derivative first. Times. Derivative of 1 is 0. Derivative of 4 sine, I think, is 4 cosine. All right? And again, I'll evaluate now at 0. Oh, I like 0. Uh-oh. Nope, no uh-oh. Never mind. All right, sine 0 is 0. Cosine 0 is 1. So I get half. Pretty sure y prime works out to be 2. And again, at this point, I have a slope. I have a point. I can quickly make a line. Y minus 0 equals 2 times. And everybody, I would actually leave it like this tomorrow on the test. I didn't say simplify. I just said give the equation in point slope form, or equation of a tangent line. I didn't say y-intercept. I suppose if you did y-intercept, it would look like that. Point is, don't do more work than you have to. All right? And again, lots of things here. Knowing the derivative gives you the tangent line slope. Knowing you can create the equation of a tangent line. All right? All right. The last thing I know from years past that sometimes shows students is stuff like this. I tell you f of x is equal to the square of the function g of x. And I say find the derivative. Well, I'll start with that this is a chain rule. So I would look for this. You bring the 2 down, right, of g of x, and the power is reduced to 1, times the derivative of the inside. So the first one is simply that. Does that make sense? The power comes down. The next one, again, it's the same rule. You always take the derivative of the outside function first, and the inside doesn't change. But then you got to multiply it by what? The derivative of the inside. And again, these are chain rules, both of them, okay? And there are examples in the book. Look at the chapter review, or even in the section where the chain rule is introduced. All right? And again, I can put trig inside these. This is a good way to test both, okay? So on the last one here, find the derivative of f of x if it equals g sine of x. Well, again, the derivative of the outside is just g prime sine of x, and derivative of sine is cosine. And even more fun later on, probably not tomorrow, would be problems like this. And they ask you to find h prime of x, okay? This one's not too bad. Again, g prime inside stays the same. Now take the derivative of the inside, which is 2 cosine x squared. But now the argument wasn't just x, right? So now you got to times it by the argument derivative, which is 2x. All right? Multiple chain rules. We're going to walk before we run, but this is stuff we got to get pretty good at. All right? So we're going to be here tomorrow. We're working towards here. All right? Last one I'm going to do today, a related rate problem. And again, the volume of a cube is increasing at a rate of 10 cubic centimeters per minute. Right there, right? Volume per time, centimeters cubed per minute at the end of the first sentence. That's your tip-off.
What's a cube again?
A cube, all the sides are the same.
Yeah.
Yep. So the lengths are all the same. Yep. So first thing I'm going to look for tomorrow is a sketch of the cube, right? And then I'll say, what are the knowns? Well, the known this time is dv dt. From the first sentence, this is what I know. All right? All right, so that's the first sentence in blue. How fast is the surface area increasing? All right, I'm going to call the surface area A. So how fast? dA dt, how fast is the surface area increasing when the length of an edge is 30 centimeters? All right. Now, the big problem on this, guys, is that we have volume and surface area. Two equations here. We're going to have to write out and see where the relationship is. All right. Does everybody agree the volume is area of the base times height, L cubed, right? And if you're not sure, cubes are pretty easy. There are 6 surfaces. Does everybody agree that the area of one surface is L squared? And if you're not sure, you'd have to draw it out as a net, I suppose, which would take a lot of time. I'm not going to bother doing that. I'm almost done, guys. Area equals, area equals L squared, 6L squared. All right. You know you want dA dt. So I can take the derivative of the green one right here, and I can get dA dt equals 12L dL dt. But the problem is when you start checking stuff off right now. I know that this is our unknown. I know L, but I don't know dL dt right now, do I? But if I take the derivative of the black one, dV dt equals 3L squared dL dt. All right. I know here that this is, again, start checking off what I know. I know dL, I know L, but I don't know this. Well, you guys see how dL dt then can be found using the black equation? I can use the black to find the one unknown. Now this will be a little harder than the ones tomorrow. So again, if I fill in 10 cubic centimeters per minute equals 3 times 30 centimeters squared. All right. dL dt. I can do the math here. dL dt equals 900 times 3, 2,700. So I get 1 over 270 centimeters per minute. And now I can pump this back into the green equation. dA dt equals 12 times 30 centimeters times 1/270 centimeters per minute. If I do the math, guys, 360 over 270, I get 4/3 centimeters squared per minute. All right, look at those example problems with the single variables. Oops, tough.